I should like get a free pass.
After
everything's done.
We are gonna be on,
I did.
hey, we are gonna be on slide number 20, and settle in, I know you've been talking and working. This is the green packet of notes, the original. The green original, we are on slide 20. So we're gonna move on to acceleration today. Give it back.
That's his.
He's like, no.
All right, so this is gonna have just a quick review of the graphing. Obviously the details and the thorough examples and things are all in, on the other set of notes. But we'll do a quick recap, so it's just kind of thorough and complete in this. Give it back right now so you're not distracting. Right now,
Okay.
Billy, whoever has it, give it back,
I'll put it back.
right now.
Learn to have it.
Thank you, good catch.
I
Okay. You guys need to get much better at focusing, yes.
I don't have a page of it, it looks like somebody did it all.
So maybe go to the blue binder and find yourself another copy. Or excuse me, the blue tub, extra papers. There you go, Barrett's getting it. Yeah, so here's the thing. You guys are scattered. You're distracted, and your work's been showing it. Hopefully it doesn't on the lab you just did, but it has been showing it. Compared to the other classes, and like they're just with me. You guys are not. Tighten it down. Fix it. Thank you. All right. So obviously we know that slope is rise over run. We have that change in vertical position is, and our change in horizontal, which is our time. Those labels match our velocity equation, which is displacement divided by time. Right? This is not new information. Obviously, we know this. Okay? We should have, actually you guys have been doing pretty good with this part of it. So really there's only two things that you have to consider when you're talking about motion graphs. You have to pay attention to what direction the line is headed. If it's up, it's a positive velocity. Down is going to be a negative velocity. Is the line straight or is it curved? Straight is going to be constant velocity. Curved is going to be changing. So this is a really nice kind of summary of what we spent last week on, right? Any luck over there? You don't have yours either?
You gotta do some push-ups. Get that back.
I mean, I don't know what to tell you. I have 5 extra copies. People apparently have used them all.
What a silly guy.
Well.
Jacob Cripples got a question.
I don't even know what you said.
This is not the appropriate time. If you guys know you don't, yep, it's those ones. Like, this is not okay. Like, people have not been bringing their correct stuff. You haven't been bringing what you need. We're cracking down. Like, absolutely not okay for you guys to be getting worse as the year's going by. You can get a little bit frustrated with you. By far, worst class for organization, doing what you need to do. It's not stapled, so you need to staple it. All right. Frustrating when you don't do what you need to do. And that's like half of you in here at some point, yes. No, not right now, I'm sorry. All right. Any question on what my expectations are for you? What I need you to do? Show up prepared. Don't lose things. You have a binder, keep track, and obviously if you realize you don't have your notes ahead of time, maybe take care of it before we're actually in the middle of notes and now you're letting the whole freshman class see that you are unprepared. Not happy. Not a great way to start the day at all. Get your act together. You do better than this. You make the choice whether you're doing better or not. If it's funny, go ahead and leave. All right? Do you want to leave? All right. So, here are our examples. If we're dealing with position versus time, the lines are showing us velocity, and we know that a straight line is going to be constant. That's like cruise control. So we see here object 1 is moving at a constant positive because it's pointing up, and because it's straight, we know it's constant. So cruise control at 55 miles per hour, for example. Object 2 Kendall? Dead, flat line, no motion, right? That perfectly horizontal line, because I get, like, these are all straight, but when we're saying flat line, we're meaning it is horizontal, perfectly flat, like that EKG monitor not having the spikes. So this is like a car that is parked. Object 3, still constant velocity because it's a straight line, but I know it's a negative velocity because it is a negative slope, it is pointing downward. And so this would be like a car maybe even going in reverse at 10 miles per hour on cruise control, which I don't know if you can set the cruise in reverse. I don't know if that's a thing, like if that's actually possible, but this is what this could be showing. This could also be showing in the car moving in a west, a down, a south, a left, or that reverse type motion, okay? All right, the last, well actually two, we're gonna cover our two last vocab terms today. Remember, vocab quiz is set for Thursday, just a reminder of that. And so the last two words we're gonna talk about today that we haven't covered are instantaneous velocity, which is a really easy idea. It's the velocity of an object at a very specific instant. So on the graph, anywhere I point is the speed or velocity at that particular instance in time. So at 1 second, I can tell you how far away or where my position was from the origin. At 4 seconds, I can tell you exactly where my position was. So it's a really kind of easy idea. In real life, what it's like is looking at your speedometer, or you know, like if a cop has a radar gun pointed at me and I'm speeding, well, that's my instantaneous speed. I could say, officer, I've been on a 1,000-mile trip. I wasn't speeding before you know, got me with the radar gun, and I won't be speeding after. It was just at that one moment. Do you think I'm gonna talk my way out of the ticket?
Yes.
Probably not. Hopefully, maybe, like I could try, but he could still say, well, at this instant, you were speeding. I don't care. I'm glad you weren't speeding the rest of the trip, and you're not gonna speed any, you know, beyond this point. But at this particular instant, you were speeding. And I couldn't argue that, like, I actually was, even if most of the time I'm not. And so again, like, it's at that particular instant. And again, it's an easy idea, I think. Nothing too shocking about it in general. So acceleration. So this is going to be the rate at which velocity changes over time. So you guys have a pretty good understanding of velocity. You did a good job of calculating velocity. You did a good job of graphing or like interpreting those graphs. Hopefully the speed lab that you just did, you did a good job of actually graphing them. So I'll take a look at that today. So now we need to look, because velocity is not always where something is like on cruise control. It's not always at a exact set steady rate. A lot of times it's going to be changing as time goes by. And so that's what acceleration is. It's when an object speeds up, slows down, or changes position, or maybe even a combination of those things. Right? And so there is an equation for this. Right? So the average velocity is VF minus VI divided by TF minus TI, also known as the change in velocity over the change in time. The only time we're going to need this extended version of the acceleration equation is if your VI or your TI is not 0. So like yesterday, when you started your stopwatch, they were all on 0, right? Your TI was 0. So we didn't need to subtract your time at 15 meters minus 0. Logically, we get it's 0 taking away from it, so you can just use the original number of maybe 4.8 for our fastest group, right? 4.8 minus 0 is just 4.8, okay? Same thing with velocity. If you start at rest or from no motion, then your initial velocity is 0. The only time you're going to need to use this version, if it specifically says you start at 50 meters per second and go to 60 meters per second. So beginning at, you're going to be looking for some of those key words, but if you have an initial velocity other than 0, you'll need to use this extended version, okay? Very, very rarely is there a time that's not zero. There will be more situations where you have a velocity that's not zero, but usually time is almost always zero for your initial, right? And like I said, that'll be the only time you use the extended. We do have a triangle. It's set up just like our other triangles, where if I'm solving for acceleration, it's velocity divided by time. If I'm solving for time, velocity over acceleration. If I'm solving for velocity, it's the only one that uses the multiplication, where it's acceleration times time. And you guys are great at using those. Okay. Typically, the units are going to be the meter per second or meter per second squared. Right? That square is because the velocity already has a meter per second as the unit, and then you're putting that over another time unit. So you have a meter over a second over another second, which is squared. Right? This is also vector. Why do you think it's vector? What do you see here that's going to tell you that? What? It has a direction. And we know that because velocity is vector, that VV, if you see velocity, then anything dealing with velocity is vector as well. So displacement, vector, and now acceleration. We have 3 vector quantities. All right, so a couple practice problems. A roller coaster starts at rest, meaning at 0 for velocity, and speeds up to 50 meters per second over the course of 17 seconds. What is the average acceleration of the roller coaster? So following our technique of circling what we're solving for, so we're kind of short on time, so I'm going to go through this quickly. So we're going to circle it in the problem. It's asking for acceleration, right? And so then we have to pick out the equation, which is just a standard one, right? It's just the change in velocity over change in time. We don't have to use a triangle to rearrange anything. So velocity divided by time. Now we're going to underline the 2 things, or the information that's given in this problem. All right, so the first thing is we have a final velocity of 50 meters per second. Right? And so it started at rest, so that's like 50 minus 0. So we really just need the ending velocity, that 50. Our time is going to be 17 seconds. And so those are the 2 variables that I need to pay attention to. Now I just plug them into my equation. So I'm going to take my 50 and divide it by my 17, and I end up with 2.9 meters per second, because this was a meter per second and this was a second. And so you have a meter per second squared. So anytime you see that square, that will make you think acceleration. Just like when you saw that cubed for the length, you thought of solid volume. So now that square should help trigger you, and you should be thinking, okay, we're dealing with acceleration now. Okay, and so velocity is the meter per second, or some version of a length divided by some version of a time. And so that's how we end up with the meter per second squared. And so as we go through these, I will show you, just like I did before, where the units come from, and kind of prove that. This is also important. If the acceleration is positive, it's going to be speeding up. If the acceleration is negative, it's going to be slowing down or decelerating. And so we have to include a negative sign. So if it says it's decelerating or slowing down, you automatically need to have a negative sign that goes with that. Okay, and so that becomes really important as we start into these calculations. Thank you for the 2 of you who checked in, that you weren't going to be here tomorrow and got the paper ahead of time. I appreciate that very much. You can wait till after our class period and take a look, and I'll have the explanation videos and stuff. So we'll stop there.